We say that this method is progressive because the new term in the UCB equation is inversely proportional to the number of times the action A has been taken from S. The fewer times we have selected this action, the higher the impact of the third term will have. Therefore, if the heuristic determines is a good action, it is likely to be picked, and vice versa. As the action gets picked more often, the third term in this equation will become smaller, independently of the value of H, and the other two terms will have a higher impact in the selection. Another widely known enhancement is all moves as first, also known as AMAF. Essentially, AMAF relies on the fact that the quality of some moves is the same independently of when they are played. This is true for some games, but not for others. But if the impact of the action is not time and state dependent, AMAF is a good improvement to use. As we'll see next, this affects the selection and simulation steps of MCTS. Let's see how AMAF works through an example. Imagine we have this tiny game of Go, where black has to move next. If black is using MCTS, a possible iteration could go through this sequence. Here's the root node with the current state where the move needs to be made. Black plays at position C2. Then white on A1. Let's imagine these two moves are still inside the tree, but it has been the selection step, the one that has indicated the moves here. Now we continue with the expansion step, which chooses B1 for black, and simulation step that plays A3 for white, and C3 for black. All these moves have been done outside the tree in this iteration. This also finishes the game with a win for black, with a score of +1. Remember that Go is a territorial game, and in this case black wins with 5 positions under control, as highlighted in the figure, while white has only 4. So far, this is just a normal MCTS playout in one iteration. We could consider, however, other alternatives that MCTS could have taken while navigating the tree. In this case, there are two other nodes in the first level that match moves down in the iteration. Note that we are not adding new nodes to the tree here. We are just considering nodes that were already there when we started the iteration. There could be other actions for the opponent's move that are also within the tree and visited during the iteration. In this color-coded image, you can see how some moves performed during the simulation step are also contemplated inside the tree. If you are using AMAF, the Q values for all these actions, B1, A3, and C3, are updated during the backpropagation phase with the reward, that is, black winning. This happens even if the specific nodes in the tree have not been visited. What this achieves is to propagate the reward of an action through its different positions in the tree where the action has been applied in previous iteration. For instance, the reward obtained in this iteration affects the average rewards of the B1 move in a node outside the trajectory followed in the The advantage of using this is not only to reuse rewards to the tree, but also to provide more information to nodes in the tree for better statistics. The confidence of taking B1 gets updated even when B1 is not selected by MCTS in level 1, if B1 is selected later down in the simulation step. The values can be updated at once, or each node can have its own alien AMF value. This way, it's possible to distinguish between the average of rewards obtained when the iterations truly went through the nodes and this bonus score obtained via AMAF update. This bonus score are normally referred as the AMAF score, and it can be used to determine different selection policies. One of the popular variants when using AMAF is alpha AMAF. Alpha AMAF keeps the AMAF score separate from the Q score computed by tree selection. The value used for UCB exploitation term is a linear combination of the traditional Q value and the other AMF score. Alpha is a parameter that allows tuning the impact of each average on the final exploitation term. While alpha AMF has itself many variants, one of the most successful ones is RAVE, or Rapid Action Value Estimate. In RAVE, alpha is not kept constant, but it decays following the particular rate shown in the equation of this slide. Alpha will be the maximum value between 0, so it's never negative, and the second expression shown in this slide. In here, V represents the number of visits a node has received before the RAVE values are used for the first time, and N of S represents the number of times this state has been visited. Note that as n of s grows, alpha becomes smaller. What this means, looking at the equation on the top of the slide, is that the exploration term of RAVE will depend more and more on the traditional value of Q of SA and less on the AMAF scores. In other words, the importance of the AMAF scores decays with time as this state is sampled more often, to end up relying on the iterations that went through the node only on the long term.